Swayam Prabha. Digital India. Educated India.
So, we have talked about radiation impedance for a sphere. Let's look at very quickly radiation impedance for an open tube. So, ideally P is exactly equal to 0, right? In reality, you can say that it's approximately equal to 0, because that change to 0, it happens over some finite distance. So, this is an open tube. Now, my impedance, I know, is equal to P over U. So, if P is approximately equal to 0, I can say that Z is approximately equal to 0 also. What does that physically mean? What it means is that when sound is traveling here, then in case of sphere, we saw that for a wide range of frequencies, it's difficult to dissipate power into free air from a spherical source because of that psi factor, and psi becomes significantly large in that case. Do you remember that discussion? Because of the power factor, the value of power factor is significant at high frequencies and also at low frequencies in case of a pulsating sphere. So, at low frequencies, you need very high energy to pump small amounts of energy into free air, and at also high frequencies, you need large amounts of input energy to pump the same thing. But in case of an open tube, given that Z is approximately equal to 0, it's relatively easier to pump energy at all frequencies into free air. So, if I have a vibrating piston here, it's relatively less difficult or easier to pump energy into free air. So, that is there. So, essentially when we construct systems which have to produce sound, then you want to ensure that the radiating impedance of that system is as low as possible, and also the overall power factor of that system. The closer it is to, psi being equal to 0, the closer is it equal to that value, the better it is, the more efficient that system is. If you want to have stronger attenuation of sound, which is the inverse problem, then you will like to construct systems which are in the other direction, so that you like to increase the radiation impedance, because that will essentially mean that less energy will get dumped into the environment and will be heard by individuals. So, there are several topologies through which sound gets propagated into the air. A very common topology is that you have an infinite baffle or a wall, you can call, and then here I have a diaphragm or a flat surface which is moving back and forth. Especially in some of the older sound systems, you would see very big boxes which will be having one speaker which is moving back and forth. Essentially, it acts like as an infinite baffle because the stiffness of the box is very low. So, this is one topology. Another topology which we have talked about is UV sphere, which is pulsating, growing and contracting. That also emits energy into air. This is another third topology, right? And fourth topology could be a plain circular piston without any baffle. So this is gone. Then how does it emit sound? So there are different approaches. So what we'll talk is a little bit more about this particular topology, what we call plain circular piston in infinite baffle. So this is my infinite baffle. And this is my plain circular piston. The radius of this piston could be R naught. R. So again, what we are trying to get an understanding is that as this piston is moving back and forth, it has a certain volume velocity, it generates some pressure. How does all that energy gets dumped into air? And that is quantified through this number called radiation impedance. So this problem, you can develop some finite element models, do some numerical experiments, and after a good amount of computational modeling, people have come up with fairly standard values. So for a plain circular piston in infinite baffle, the radiation impedance looks something like this. It's a bunch of one capacitor, two resistors in series, and an inductor. And this is for impedance models. For mobility model, the circuit looks, now that you understand the idea of a dual, it looks something like this. This is MA. Okay. And the values of these elements have been computed, and so the value of RA1 is 0.1404 times rho naught C over R naught square. RA2 is, what happened to my stylus? So RA1 is 0.141 rho C over R naught square. RA2 is this particular expression. MA is 0.27 rho naught over R naught. And CA, another constant, is 5.94 R naught cube over rho naught C square. And because now we are talking about specific constants, 0.14, so these relations are good to the extent we are in SI units. So R naught has to be in meters, rho naught C has to be, rho naught is density, so it's kg over cubic meters. C, which is velocity of air, has to be meters per second. Otherwise, these relations have to be adjusted. And RA1 lowercase ra1 and lowercase ra2 are basically just inverses of uppercase values. So if you have a pulsating membrane fixed in on a big surface, and air from back side is disconnected with air from the other side from your room, then if you use this model, then it will fairly accurately capture the radiation impedance of that membrane. So what we will do is we will look at it, and so this is mobility model. Now what we will do is we will see what are the characteristics of this particular model at low frequencies and at high frequencies. What does this mean physically? So if I am in very high frequency land, when omega is large, well, let's see what's going to happen. So when omega is large, MA becomes extremely large, so very little current goes through here, so I can drop this out. So the current has choice between going through RA1 or through this capacitive element. At very high frequencies, the impedance offered by capacitor will become very low. So current will prefer to go from CA and then it goes through RA2. So my equivalent circuit at very high frequencies becomes this is my potential difference P, and the current is volume velocity, and this is RA2. So what this shows is that when I have high frequencies, a piston mounted on an infinite baffle behaves like a purely resistive circuit. So the first thing is that the inefficiencies associated with that power factor, they become minimized at high frequencies. Because I don't have any inductive or capacitive element which alter the phase. That is one thing. The other thing is that in the near field, again, what this shows is that the transmission of sound happens in kind of like a beam, because this impedance is something very similar in nature, qualitative nature, to plane waves as they are moving through tubes, open tubes, infinite long. Right. If you remember, the impedance in a open tube is purely resistive thing, and it does not attenuate in strength as you move forward. The strength of sound as it moves in an infinitely long tube, it does not decay with traveling. What this shows is that it's the same thing happening here also. So what that means is that at high frequencies, the behavior of sound is like a beam. It travels like a ray of light at high frequencies. This is what it means physically. Now, of course, when you go away from the source, when you are in far field, then it again starts to radiate. But for a fairly good amount of distance, sound moves like beam at high frequencies. This is the physical understanding. So that is case 1. Case 2 happens what if omega is low? Omega is small. So what happens? Let's look at this circuit again. When omega is small, I can fairly easily drop this term out, CA. Right. So what I'm left with is MA and RA1 and RA2. At extremely low frequencies between RA1 and RA2 and this mass, it will still prefer the inductive part. So in a little more general sense, I can say that my circuit will be something like this. So for extremely low frequencies, current will still like to go through MA, which means that for very low frequencies, the dissipation of power through an infinite baffle will be very less. Energy will go into the system, back into the system. It will not get dissipated. So it is very difficult to dissipate for very low frequencies sound into free air using an infinite baffle. All what you are seeing is that different approaches of dissipating low frequency sound into medium is not an easy thing. It's efficiently doing the same thing efficiently is not easy. Similarly, attenuating low frequency noise is not easy. You will see later in the course. So what we will do is we will, yeah.
So in the first case, why haven't you considered capacitor?
In the first case, so you understand why I dropped out MA, right? At high frequencies. Now at high frequencies, capacitance, the impedance offered by capacitance will be virtually zero, because it's 1 over S times CA.
Yes, but still will be there.
It will be there, but at high frequency, the impact of that.
Neglecting the magnitude with respect to RA2.
Yes, with respect to RE2. What I mean, I can keep on increasing the frequency, and I will hit a number where it will be small enough compared to. So what that crossover point is will depend on the ratio of RA2 and CA, right? So you have to figure that out. But at high frequencies, CA you can ignore it and replace it by a short.
So can you repeat the point that you mentioned about attenuation of low frequency sounds and the other equivalent in making the sound at high frequency?
Yeah, what we have seen is that when we try to dissipate sound through some of these sources into free air, what we are seeing again here is that at very low frequencies, MA dominates. All the current goes through MA, which means that the dissipation of power is less. So all what happens is energy goes back and forth into the system. We had seen earlier that the average power dissipated in general is essentially dependent on the R term. If very low energy is going through R, the energy dissipated into the sound, into free air will be very less. That's what I'm saying. So what we will also do is here, we will compare the efficiency of this system for low frequency with a spherical source. Is a spherical source easy to dissipate power into free air, or is it easier to do it using an infinite baffle? That's what we will do. So this is for infinite baffle. Now for a spherical source, we had developed a relation something like this. The impedance was this is the radiation impedance for spherical source. Okay. So if the size of the source, both the sources are same, that is RO is same, then let's look at the numbers. So we'll construct a small matrix. Spherical source, and the other column could be infinite baffle. And what I will do is I'll list R and L. So again, the circuits looks very similar. You have a resistor and an inductor here in parallel, same thing in case of a spherical source. All we will be doing is comparing the magnitudes of these elements and see how they look like. So in case of spherical source, the resistive value was Z0 over A that equals over 4 pi r naught square is 0.084 rho c over r square. That's my number, 0.084. In case of infinite baffle, it is 0.458 rho naught c over r square. Okay. The inductive value will be z naught r naught over 4 pi r naught square, and if I do the math, it comes approximately to 0.084 rho naught over r naught. I just assume pi to be 3. So it comes close to 0.084, maybe 0.083. In this case, it comes to 0.27 rho naught over r naught. Okay. So what do you see when you look at these numbers? That the impedance offered by a spherical source is substantially less for the same size of the object, substantially less than that offered by source of sound mounted on a baffle. So spherical source by itself is not a very efficient way to disseminate sound into air at low frequencies. An infinite baffle is even poorer approach of disseminating sound at low frequencies into the system. This is because your R is less, your L is less. For a spherical source, your baffle's numbers are significantly higher, 5 times or more. So we have talked about spherical sources, we have talked about radiation impedance of a tube at the end of it. So now we will very quickly consider radiation impedance for a plain circular disc in free air, if it moves back and forth. So for low frequencies, I'll very quickly give the impedance circuit looks something like this. So this is my impedance model. So my across variable is pressure. Here my through variable is pressure and across variable is volume velocity. And R is 0.019. So R square times density times omega over C cube, and mm equals 0.271 times rho naught over r naught, and in this case R equals 0.261 omega square r naught 4 over rho naught c cube. You see that things start getting more and more complicated. So you'll find a more exhaustive list of some of different geometries and what each of these geometries have for their radiation impedance in a book like Baronet, which is the prescribed test for this course, reference test. and for high frequencies the circuit looks simply like this. Where R equals to rho naught C over pi R naught square, and this is valid for which model? Impedance or mobility? Which one? Impedance. So if I have to use for high frequency something similar for mobility, what will I do in that case? R will get replaced by its inverse. Okay. So what we will do is one example and see how radiation impedance improves our prediction of some of the acoustic properties of systems. So let's consider a bottle. This is actually a physical bottle which I measured. So it has two parts. It's a badly built bottle. So there's a volume here. This length is L1. Let's call it L2. This length is L1. Its mouth has a diameter of 2 times R1. Okay? And the volume has a diameter of 2 times R2. So what I would like to know is what is the natural frequency of this bottle. This is the volume is like a stiffness member, and the open tube on top of it is like a mass, right? So it is kind of a mass spring system, and I like to see how good my model is in terms of predicting. So we'll put some numbers. L1 equals 6.7 cm. R1 equals 1.43 centimeters. Volume of the lower portion is 530 times 10 to the power of minus 6 cubic meters. I mean, I can also find L2 as P naught over pi R2 square. So first thing I'll check is that is my all these lengths significantly smaller than what number? Lambda over 2 pi, right? So L1 has to be less than lambda over 2 pi, which gives me a frequency number corresponding to 819 hertz. Is everyone sure how to jump from lambda to f? Right. So what this means is that if I am significantly below in frequency from 819 hertz, then if I approximate my tube, which is L1 long, as an acoustic mass, I'll be okay. That is what it means. Similarly, L2 has to be less than lambda over 2 pi, which means frequency equals 365 hertz. So if using this mass spring approach, if my resonance exceeds 365 hertz, then my model is not valid. Basically, that's what it means. So now we'll find what is the frequency of this system. So if I construct an impedance model, pressure that is my mmc. Oh, I'm sorry, it's acoustic mass. So MA, we have seen from earlier lectures and discussions, is rho naught L over pi R naught square, and my capacitance value is, or acoustic stiffness is, V naught over rho naught C square. So my Z bottle is S times MA plus 1 over S times CA. So if I plot its poles and zeros, I have a pole at 0 and a pole at origin, and I have two zeros symmetrically along the imaginary axis, and this value is 1 over MACA. When I do the math and I plug in all the numbers, my first estimate on frequency resonance F naught comes to be 210 hertz. And when I actually did the measurement, so FM, it was 233 hertz. I should have shown this here. So this is clearly, it is off. And in terms of estimation on frequencies, they shouldn't be off by this much of an amount. Frequency estimates come fairly close to reality. So next we will see how we can improve our model to get a better and closer estimate. So what we will do is, I went to this book Beranek and I said, okay, there's this tube. I have just modeled it as a pure mass element. Okay. But there is some radiation. This is a tube, but it may be seeing some radiation impedance here because it's dissipating sound into free air. So what is that value? So once I do that, my refined circuit becomes something like this. So I still have my, this is MA, which we have already calculated. This is CA, and then I put, so the extra elements based on more rigorous computational modeling are these terms, R1 and M1, where R1 is 0.479 rho C over R naught square, and M1 is 0.195 rho naught over R naught. So putting the values of R and everything in this, I get R1 equals 953 times 10 to the power of 3 Newton second over meter 5, and M1 is 19 times 10 to the power of 3, something like this. So for low frequencies, clearly R1 is very large compared to M1. Okay, so I have to make correction here. This is omega M1. omega m1 for, I just chose a small number, 190 hertz. Because I said 190 is fairly close to 230. So I wanted to get an estimate that in the neighborhood of resonance, which term is dominating, R1 or omega m1. So what I am seeing is that in the neighborhood of resonance, this is very small, this is very large. These are in parallel. So what that means is I can drop R1 out at around 190, 200 hertz. So then my approximation of this circuit becomes MA, M1, C. I still have pressure. So I get these three elements. Is everyone comfortable with why I dropped the R term? So I know M1, I know MA, I know C. So my second, I tried to get different estimates. So my second frequency estimate, natural frequency estimate, came to be, what was it, 219 hertz. So I was able to improve my estimate from 210 by another 10 hertz or so. So that is how close I got to the actual number. After that I did not bother. So what this shows is that incorporation of radiation impedance in your actual model will help you get a better picture of how the circuit is going to behave. Because the outside space does impede flow of sound as sound emanates from a vibrating member or a tube or whatever. So some of these elements have to be captured in your circuit analysis. So that is all I wanted to talk about today. Starting next lecture, we'll start talking about more detailed analysis of the whole speakers, microphones and so on and see what they show us.